Hello and welcome to Algebra 1 with Miss Betsy. I'm glad you're with us today. We're going to be talking about expressing square roots today. Before we get into our new material, which is actually from Chapter 10 in our Algebra 1 text, we're going to go back and review from way back at the beginning of the year. We're going to go back to Chapter 2 where we were talking about how to express square roots of perfect squares, and we're going to get some of our vocabulary reviewed so that we can understand exactly what it is that we're talking about. Because we've seen time and time again in our study of algebra that the concepts and the execution of a particular process or the solution of a particular problem wasn't so difficult to arrive at, provided you knew the meaning of the definitions of the words, so provided that you knew your vocabulary. So I want to make sure that we go ahead and get a good review of that before we start. First, however, I want to go back to a lame joke from an old video that I was watching. And can you tell me what it is that is the very most favorite game that baby bunnies like to play? They love playing hopscotch. So we're going to be talking about finding the square root of a number. Square root is indicated by this funny looking sort of a check mark over here. This is called the radical symbol, radical sign. And there are no numbers indicated, it's just this little check mark here. And you'll remember that a square root is all that it actually is. It's one of a number's two equal factors. And you remember the factors are the things that you multiply together to come up with a product, or the answer to a multiplication problem. So how can we factor 4? Well, this here says that the square root of 4 is the same as the square root of 2 times 2, because 2 times 2 is 4. It can also be the same as the square root of negative 2 times negative 2, because when you multiply two negative numbers together, you get a positive 2. We also can factor 4 into saying the square root of 4 times 1, because 4 times 1 is equal to 4. Now, if we're actually going to calculate the square root of a number, what does it say first? It says, well, the square root is one of a number's two equal factors. We have the same factor here of 2. We have the same factor here of a negative 2. These two factors here, while their product is 4, the factors are not equal, so you cannot use this factorization of 4 to arrive at a square root. So we have two choices now, don't we? We can say that 2 times 2 is equal to a positive 4. A negative 2 times a negative 2 is equal to a positive 4. So we have two possibilities here when we're calculating square root. Square root is just one of the number's two equal factors. So the square root of 2, we have two possibilities here. We could say that the square root of 2 is equal to 2, or the square root of 2 is equal to, the square root of 4 is 2, or the square root of 4 is a negative 2, because 2 times 2 is 4. Negative 2 times negative 2 is also a positive 4. Is the square root 2, or is it a negative 2? Well, here's where we have a little bit more vocabulary. The positive square root is what we call the principal square root. Principal square root. The negative square root is a very creative name here. It's the negative square root. When you're talking about square roots, you're always going to have two choices. It can be positive or negative. And later on, as we get a little bit closer to the end of Algebra 1, you'll see that solutions frequently use the notation plus or minus the square root of 7. But we're not going to be talking in this class today, or for a while yet, about plus or minus the square root. We're just simply referring to the square root of a number. Now, if we haven't specifically told you which root we want you to take, we're always looking for the positive number, the positive root of a number. we're always looking for the principal square root of a number. So if I say to you, give me what is the square root of 100? While it's true that -10 or +10 are both roots of 100, square roots of 100, I'm wanting you to tell me that the square root of 100 is 10 because I'm looking for the principal square root. Okay, now let's look down here. You remember way back with this little 3 here, this is called the cube root of 8. Now if a square root is looking for one of a number's 2 equal factors, what do you think a cube root is going to be? Yeah, a cube root is one of a number's 3 equal factors. Now when you're taking cube roots, are you ever going to have a negative root, like have a negative square root? Why not? Well, you're not going to have one because -2 times the -2 is a +4 times the -2 is a -8. You can never have an odd number of negative factors that result in a positive product, because every pair of negatives is positive when you're multiplying them together. But if always and forever, when you have a positive factor and a negative factor, the product's always going to be negative. So all of that summarizes into cube roots are always positive. Now, there's a little bit of notation here, a little bit more vocabulary. What's this symbol right here? We have the cube root of 8. Well, this is a radical number. And we're going to see that we have an index, we have an exponent or a power, and we have a radical sign, we have a radicand. So we have to be able to identify all of the parts of this radical. So we have the cube root of 8. What are all of these different parts? This check mark thing itself, we just finished saying that this was the radical sign. This number here is what we call the index. The number that sits underneath that radical sign, this is called the radicand. And let's just say that we had the cube root of 8 squared. And don't worry about calculating it because you can't. If we had the cube root of 8 squared, well, that little exponent there, you can also refer to that as the power. Not everybody does that, but I'm going to use that expression. I'm going to call the exponent of the radicand as the power underneath the radical sign. If you don't know this vocabulary, learn it. You have to. You have to know the index. You have to know the radicand. The index tells us what root we are finding. We're finding the cube root or the 4th root. This right here is square root. Just like if we have x all by itself, I know that I'm talking about 1x. The coefficient is understood to be 1. With radicals, if the index is not showing, it's understood that's the square root. We have the cube root. We have the 4th root. I'm going to put an n in there. We have the nth root. We just have some strange sounding vocabulary. You have an index, you have a radical sign, which means we're taking a root. All a root is one of the numbers, however many equal factors there are. If it's a square root, it's one of the number's 2 equal factors. If it's a 4th root, it's one of the number's 4 equal factors. Square root, cube root, 4th root, 110th root. No, I don't know why in the world you'd want that. Maybe in some really bizarre application you would. But that's all we're talking about here with roots. Radicand is the number underneath the radical sign. Index is the number that tells us which root we are taking. You can have square roots of rational numbers, square roots of irrational numbers. Let's think what it is that a rational number is. Remember, way back at the beginning of the year, we talked about different subsets of numbers. You can have integers, you can have whole numbers, you can have natural numbers, you can have rational numbers, and rational numbers are numbers that can be expressed as a ratio, okay? Numerator divided by denominator, and when that divides out, the decimal representation of that, divides out evenly, okay? And rational numbers could also be an example of a repeating decimal. This here is what we call a terminating decimal. And then we had, for example, the rational number 1/3. When you do the division to convert that into a decimal number, your division goes on for now until Jesus comes. It's 0.3333333. So this little bar above the 3 indicates that that 3 repeats forever. So we call this a repeating number. And both of these two types of expressions, these are rational numbers because they can be divided into either a terminating decimal or a repeating decimal, where you recognize the pattern that it comes on forever. So these were rational numbers. Then we also had something that we're just going to talk about a lot more now. These are rational. And now we're going to talk about irrational numbers. And an example of an irrational number would be pi. Pi is a constant that is used a lot when dealing with circles or spheres. And pi, when you calculate it out, we say that it's approximately equal to 3.14. 3/4 is exactly equal to 0.75, because when you do that division, it stops, you're finished. When you calculate pi, that's just an approximation, because pi is 3.141592668. Whatever that pattern is, whatever that series of numbers is, it just goes on forever, and there is no pattern to it. This never ends, it's non-terminating, and it doesn't repeat. So irrational numbers are non-terminating and non-repeating. And what we're going to be working with today is we're finding rational roots and we're finding irrational roots. And the rational roots that we're working with, reviewing first, that we just did, was like square roots of perfect squares. And we said, go ahead and take the time to memorize your perfect squares, ideally up to 20 squared. 12 squared is 144, 16 squared is, 16 squared is 256, 7 squared is 9. Those are perfect squares. So you can take, if you have a root that you're taking, a square root of a perfect square, it's a rational number. Let me show you what I'm talking about. Square root of 16, that's a perfect square, because 4 times 4 is equal to 16. So the square root of 16 is rational. It can be expressed as a decimal that terminates or completes. This is 4. However, if I were to ask you to find the square root of 17 for me, that would be another matter altogether, because we don't know what number it is that multiplied by itself equals 17. There is no such number known to man. So the square root of 17 at its most exact answer is the square root of 17. The square root of 16 is equal to 4. The square root of 17 is just the square root of 17, and this is what we call irrational. And we're picking up now in section 10.1 of our text, Algebra 1 for Christian Schools, published by Bob Jones University Press, 2nd edition, chapter 10.1, where we're talking about expressing roots, expressing square roots specifically today. And we're going to be dealing with irrational roots. We should already know how to take roots of perfect squares. So we've reviewed that material, reviewed our vocabulary, and now we're going to go ahead and pick up on page 396. And I've been talking about this a little bit. Introducing the fact that we have irrational irrational roots. And we reviewed that irrational numbers are those can't be expressed as fractions because they're non-terminating and they're non-repeating. Most of the time when we're working in algebra, when we're working in any science, when we come to something that says the square root of 7, which is an irrational number, this is exact. And they're going to leave this to be your answer, because we can't get any more exact than that. Sometimes, however, they're going to want to come up with an estimation of the value for an irrational root, or they're going to want to know what two integers, the square root of 7 lies between. So let's think about what we want to do here. How are we going to know what two integers the square root of 7 lies between? Well, let's think. Square root of 2 squared is 4. 3 squared is 9. Our radicand is 7, so 7 fits right in between 4 and 9, doesn't it? So we can write that 4 is less than 7, which is also less than 9. Perfectly legitimate, perfectly true statement. Now, we can also say, because we're applying the same process to each one of these steps, we can say that if it's true that 4 is less than 7 and 7 is less than 9, it's also true that the square root of 4 is less than the square root of 7, which is also less than the square root of 9. Square roots are all in the same relationship to one another. But now is when we have the rational and irrational things. Square root of 4, that's rational, isn't it? Because we can say that the square root of 4 is 2. And the square root of 9 is also a rational number because that's 3. So we have 2 is less than the square root of 7, which is less than 3. Square root of 9, square root of 4 are rational numbers. The square root of 7 is not, so we leave it sitting under, leave it expressed with the radical symbol. So right here is the solution that we have if we were asked to find which two integers, between which two integers does the square root of 7 lie. Okay? Now, however, we could also have a problem that says find the square root of 7 to the nearest tenth. To the nearest tenth. How are we going to do this? We can't, there is a way that you can do some calculation, but at this point, how are we going to do that? You're simply going to use your calculator. calculator, there's a square root key on there. And you're simply going to put in 7, press your square root key, and you're going to get something that looks like this. 2.645, 2.6457513, and it's going to stop. It's going to stop at the limits of the display on your calculator or your computer. But you look here, there's no pattern. You can divide this thing forever, and there's not going to be any pattern discernible to what the square root of 7 is going to be. Punch it into your calculator, round it to the nearest place. Round to the desired place. Here we are told to give this, to find the value, or to find the square root of 7 to the nearest tenth. The nearest tenth is 6. We look at the 4, which is in the hundredths place, because it is 4 or less. Our rounded answer here is going to be 2.6, and we are going to say that the square root of 7 is approximately equal to 2.6. The little wavy equal sign means that it's approximately equal to. You can't say that the square root of 7 is equal to 2.6 because it's not. This is not an exact answer. And then we already did just a little bit ago the problem where it says estimate the square root of 7 to the nearest integer, but let's go ahead and do a different one. Let's go ahead and do estimate the square root of 129 to the nearest integer. Estimate square root of 129 to the nearest integer. This is when you remember your perfect squares. We want to figure out what two perfect squares that radicand of 129 lies between, where it's sandwiched in there. Well, 10 squared is 100, 11 squared is 121, 12 squared is 144. 144, 121, 100. Where does 129 fit in between these? 129, of course, fits in between 121 and 144. We're going to take the square root of both sides, the square root of every portion of this. Square root of 121 is less than the square root of 129 is less than the square root of 144. Once again, we have two rational square roots, one irrational square root. And what's our final answer going to be? Our final answer will be, let's just go this way, 11 is less than the square root of 129, which is less than 12. See the two distinctly different answers here? This one says find an irrational root rounded to the nearest tenth. This is the only time you're going to use your calculator. This problem here says estimate it to the nearest integer. And you say, well, it's somewhere between 11 and 12. 129 is closer to 121, so maybe it's 11.1, maybe it's 11.2. But we know that someplace in between 11 and 12 is the closest integer approximation of the square root of 129. So that's what they're going to have you be doing. Now, we're going to do something that's just a little weird. Very strange, actually, when you see it for the first time, and I even find it a little bit strange myself. We know how to deal with exponential notation. We know how to multiply together exponentials that have the same base, don't we? If you had x squared times x cubed, Now when you first learned how to do these, you thought, oh, well, that's easy, that's x to the 6th, because we're multiplying. But we learned pretty quickly that that's not the result of x squared times x cubed, because when you have this exponent here, this 2 means that we are using x as a factor twice, and the 3 means that we are using x as a factor 3 times, and that exponential notation is simply shorthand for how many times you use any one particular value as a factor. X is being used as a factor 5 times here. So when you have exponential notation and you're multiplying bases with like exponents, what did we do? We just added the exponents together to say that x squared times x cubed gave us a final value of x to the 5th. We didn't have to go through and write out all of the many times that these factors were used. Well, we're going to use this and we're going to see something really strange. We've only used exponents now that are whole numbers. We had some negative exponents, but they were always whole numbers. And what we're going to see now is that you can really have fractional exponents. And when those fractional exponents are used, that's when we're dealing with radical symbols. We're finding the roots of a number. So let's just look at these 2 bits of material that I'm going to give you from our text. First, I'm going to say that the square root of 4 times the square root of 4 is equal to 2 times 2, which is equal to 4. Makes sense to you? We know that the square root of 4 is equal to 2. 2 times 2, we know that equals 4. Now, we also know from what I just showed you that when we are multiplying exponentials together that have like bases, you keep the base and you add the exponents. So if we had something pretty weird looking like 4 to the 1/2 times 4 to the 1/2. Looks weird, but it still fits the pattern. It's a base and an exponent that we're multiplying together. What does our exponent rule tell us? It says keep the base and add the exponents together. So you have 4 to the 1st. 4 to the 1st, of course, is 4. Square root 1/2 exponent. What there's a strange little proof of in your text that I'm not going to take the time to show you is the truth of this statement that the square root of 4 is equal to 4 to the 1/2. These are 2 different ways of representing the same value. Square root of 4 is what they call radical notation. Radical notation. And this is fractional. Or this is exponential notation. Exponential notation. Having a hard time. 2 different ways of expressing the exact same identical value. Square root, radical notation, exponent, a fractional exponent notation. They mean the same thing. Now, let me go ahead and show you another definition here. This is something that you're simply going to have to learn and be able to apply this. And it looks weird, but it's a pattern that you can learn to recognize. And this tells us that if we have a base with a fractional exponent, base that we put the exponent in rational form where it looks like a fraction, x to the a over b, that can also be indicated using a radical symbol. The denominator is I'm not sure where that 5 came from. The denominator is the index. The numerator is the power. The denominator is the index, and the numerator is the power. You can convert back and forth from the two different types of notation by remembering that the index and denominator are the same, the numerator and power are the same. Okay, we're just going to have to practice with this, work through these. The more you deal with problems that have a fractional exponents, the more quickly you'll be able to gain some comfort with this. So let's go ahead and think about something for a moment. This is the definition that you have to have memorized. Matter of fact, let me go ahead and write this over to the side and we'll refer to it. And we will say that if you have x to the a over b, that can also be expressed as with a radical sign this way. And you're so going to laugh when I read this to you. X to the a over b is equal to the bth root of x to the a. You don't have to be able to speak that because it's just a bunch of gibberish. But you have to understand that if you want to go back and forth between those two notations, you have a fractional exponent, that the denominator represents the index, or which root you're taking. The numerator represents the power of the expression inside that radical sign. Okay? Let's go ahead and look on page 298. And the problem here is being very, very specific. It says, simplify the cube root of 8 using exponential notation. Simplify the cube root of 8 using exponential notation. Now, at this point in our study of algebra, I expect every single one of you to know that the cube root of 8 is 2. The cube root, we are just looking for one of a number's 3 equal factors. 8 is equal to 2 times 2 times 2. So the cube root of 8 is 2. 2 is one of a number's 3 equal factors. But that's not what they're asking you to do. They're not saying for them to tell you, okay, have you learned your perfect cubes? What's the cube root of 8? They want you to simplify this expression using exponential notation. And what you're going to see happen a lot of the time when you're dealing with radicals is that, you know, we have this preconception of what it means when something is simplified is that it looks neat and tidy and clean and easy. Some of the simplified radicals look anything but simple because they're messy. They have radical symbols, they have powers, they have indices, but there's a very specific definition of what a simplified radical is, and we'll deal with that in the next lesson. But for now, this says simplify the cube root of 8 using exponential notation. So what are we going to do? Well, first, we're going to change from radical notation into this exponential notation. What's the base of our exponential notation going to be? It's going to be that number that's underneath the symbol. It's going to be the radicand. So we have 8 and the exponent would be 8 to the 1/3. Really doesn't help us a whole lot, but let's think of another way, because we don't know how to simplify that. X to the 1/3 means nothing, but we can say that the cube root of 8 is the same as this. Okay, this is true, but it's not helpful. So what can we do next? Well, let's think again. Is there another way that we can express 8? There is. We can say that 8 is equal to 2 cubed, isn't it? 2 times 2 is 4 times 2 is 8. So it would be true then that the cube root of 8 could be expressed as the cube root of 2 cubed. Stay with me here. All we did was substitute in an exponential expression, 2 cubed, for the 8. Now we have all that we need to do to finish solving this problem, because we now have a radical representation that we can convert into exponential form. What is our base going to be? Our base is going to be the 2. What's going to be our fractional exponent? Well, the denominator is a 3. The numerator is also a 3, so we have 2 to the 3 over 3. Well, we always simplify fractions, don't we? What's 3 divided by 3? So that's the same as 2 to the first, isn't it? 3 divided by 3 is 1, and we don't ever write an exponent of 1. We understand that 2 to the first is the same as 2. So what we did here was we used exponential notation to simplify this by saying that 8 has the same value as 2 cubed. It's just 2 different ways to represent it. We substituted that 2 cubed in for the value of 8. And then we were able to use our rule over here that says this is what it looks like in radical form, this is what it looks like using exponential notation, to come up with 2 to the 3 over 3, which is 2 to the first, which is 2. Pause it, take a break, go get a drink, come back, look at it again. This is the type of manipulation that you need to be able to do and to be comfortable with. So while you're pausing and clearing your head, see what our next problem is. And this says, my glasses are not real cooperative, change 3 to the 1/3 x to the 2/3. 3 to the 1/3 x to the 2/3, and it says change this to radical form. Okay? Radical form. Do you remember that x to the a over b is equal to the bth root of x to the a? So which one of these two forms do we have? We have our fractional exponential notation, don't we? Fractions as exponents. What's going to, and we want to change it to radical form. We want it to look like this. Okay, so we know we're going to have a radical symbol in here somewhere, don't we? What is our index? Which root are we taking? Well, the index is the denominator. The denominator is going to have to be the same, but here this tells us that we're taking the cube root of something. What are we taking the cube root of? We're taking the cube root of what we're using as the base. 3 and x. What's the numerator of the fractional exponent of the 3? It's a 1. So we have the cube root of 3 to the first. What's the numerator of the x? It's a 2. Of 3 to the first x squared, which is equal to the cube root of 3x squared. Because 3 to the first we simply write as 3. I don't know how to teach this differently to you except to say, here's the pattern, recognize what's going on. We're taking the cube root of this base, and we're using these numerator expressions here as the powers of what we're taking root of. Now, is there some real-life representation of the cube root of 3x squared? Maybe in some applied math there is. I don't know what it would be. This is just an algebraic answer that we're looking for right now. We're learning how to go back and forth from exponential notation to radical form. Okay? So now, instead of changing to radical form, we're going to change to exponential form. So it means then, of course, that we have the radical form. So the radical form that we have is the 5th root of 4x cubed y squared. 5th root of 4x cubed y squared. Now, there's no number we can come up with it if you say this times this times this times this times this, you equal 4, because we just go 2 times 2 is 4, and that's only a square root. But there's some number out there that's the 5th root of 4. We want to write this expression, this right here is radical form. We want to change it into exponential form. So I really recommend that as you're learning how to do this manipulation back and forth, and until you have learned the pattern, radical form, go ahead and write it out. B root of x to the a. Exponential form, x to the a over b. All right? Now, we have our radical form. What's our base? Our base is 4xy. I'm going to space it out here because exponential form means each one of these little individual factors in here has an exponent. The denominator is always the root that we're taking. So what's our denominator going to be? The denominator is going to be 5. So all of these are going to be 4 to the sum fifth, x to the sum fifth, y to the sum fifth. How do we determine what the numerator is? The numerator is the power of that factor within the problem, underneath the radical sign here. We have this radicand. You have each individual factor in the radicand. The power is the numerator. Or the numerator is taken from the power here. So what's the power of 4? It's first. What's the root? It's the fifth. 4 to the 1/5. What power? 3. What root? Fifth. X to the 3/5. What power is y? 2. What root? Fifth. This strange conglomeration of fractions, whole numbers, variables. This is exponential form of this radical here. You simply have to be able to convert back and forth from one form to another. That's what exponential notation is all about. And radicals, particularly dealing, these are irrational numbers. There's not a perfect number that you can come up with these. Okay, we're going to take a breather from this and end up with something that is much easier. I think the author of the text took pity on you and said, okay, we'll close out with something easy. Let's rewind for a moment, and it says, find the integers, or actually let me go ahead and ask this question. Find the integers between which, the square root of 50 lies. That'll be good. Find the integers between which the square root of 50 lies. How did we say we were going to do this? We're going to use our perfect squares. 4 squared is 16, 5 squared is 25, 6 squared, 7 squared is 49, 8 squared is 64. So we would say square root of 49 is less than the square root of 50, less than the square root of 64. So you would say 7 is less than the square root of 50, which is less than the square root of 8. That's what we talked about already in the first part of this lecture. So you know how to find the integers between which a square root lies. Well, what if they tweak the problem just a little bit and they say the integers between which the cube root of 50 lies? What do you think you would have to do for that? Well, let's take the cube root of 50. And we picked perfect squares here. Let's pick perfect cubes. Okay, 2 cubed is 8. 3 cubed is 27, and not 2 to the 7th. 3 cubed is 27. 4 cubed is 64. 5 cubed is 125. You don't have to learn as many of the perfect cubes as you did perfect squares because the numbers very rapidly get pretty big, don't they? What are we trying to find? We're trying to find the integers between which the cube root of 50 lies. Which numbers do we have? We've got 27 and 64. 27 is less than 50, which is less than 64. So the cube root of all of these numbers, the relationship between them is still the same. It's consistent. The cube root of 27 is rational. It's 3. Is less than the cube root of 50, which is less than the cube root of 64, which is another rational number, which is 4. Same process, same exact procedure, finding the integers between which a cube root lies. Same thing also if it said find the cube root of 50 to a particular decimal point, you would use your cube root key on your calculator to come up with an approximation that you rounded to the nearest tenth or nearest hundredth, whatever they were asking you to do. So what we did today was give you quite a lot of information. We did a basic review of finding perfect square roots. We reminded ourselves that we have the radical sign, we have a radicand, we have an index, we have a power, vocabulary that we need to know. We saw principal square root is always positive. You have the negative square root. And then we talked about this exponential notation of roots. And that you could indicate, you could represent the root of a number in 2 different ways. I'm going to take the last screenshot here for you. It says if you have the root of a number that is expressed like this, you can also express that in exponential notation with a fractional exponent. For example, if you had the cube root of 16 squared, you could also express that as 16 to the 2/3. You have to be able to go back and forth between these 2 types of notation. There's no substitute for it. You have to apply whatever brain power you have, whatever amount of study time it takes to understand radical notation and exponential notation. Okay? Hang in there. Y'all can do it. I will see you next time.